Hey guys, Dean Chase here with another geometry lesson for you. Hope you're all doing great. Let's go ahead and get this thing started with a word of prayer. Dear Heavenly Father, thank you for this day. Give us, Lord. Thank you for all you've done. I pray you'll bless us with a good afternoon or evening or whatever time it is, and just help us all continue to learn. We love you, Lord. In Jesus' name we pray, amen. Hi guys, so today we're going to be learning how to use isosceles and equilateral triangles. This is page 4.7, lesson 4.7, page 264 out of your book. Let's go ahead and get started. So in lesson 4.1, you learned that a triangle is isosceles if it has at least two congruent sides. When an isosceles triangle has exactly two congruent sides, then these two sides are its legs. The angle formed by the legs is the vertex angle. The third side is the base angle of the isosceles triangle. The two angles adjacent to the base angle are called the base angles. Sorry. So here you have an isosceles triangle. I like to think about it like a mountain. The legs are the sides of the mountain. The top is the vertex of the mountain. And then the two angles on the bottom formed here are the base angles along with the base of the mountain. Okay? Let's keep going. Theorem 4.7, base angles theorem. If two sides of a triangle are congruent, then the angles opposite them are congruent. So here we know that side AB is congruent to AC. Thus, you know that angle B is going to be congruent to angle C. Converse of the base angles theorem is the opposite. If two angles of a triangle are congruent, then the sides opposite them are congruent. So here you have angle B is congruent to C, so you know that AB is congruent to AC. Pretty simple, okay? Hope that makes sense. Let's go ahead and keep going. Example 1. In triangle PQR, PQ is congruent to QR. Name two congruent angles. So here we know that this is an isosceles triangle. These are the legs. PR is the base. Q is the vertex angle. P and R are the base angles. So if we know it's isosceles, we know that the base angles are congruent. So we can say that angle P is congruent to angle R. Okay? Pretty simple. Hope that makes sense. Let's go ahead and keep going. This is a proof of the base angles theorem. Proof of the base angles theorem. You can pause it and read through it. I'm not actually going to read through this, but it's always good to read through a proof to kind of get the logical sequencing of proofs. Let's keep going. Corollary to the base angles theorem. If a triangle is equilateral, then it is also equiangular. So if you have an equilateral triangle, it means that all the angles are also going to be congruent. Okay? Which also means that all the angles are going to equal 60 degrees. Okay? But that doesn't say that there. But that's just good to know. Corollary to the converse of the base angles theorem. If a triangle is equiangular, then it is equilateral. So if you know all the angles are the same, you know all the sides are going to be the same. Okay. But just because you know two triangles are equiangular does not make them congruent. We need to remember that because you could have different lengths for sides. Okay. But if all three sides are the same of two triangles, you can prove they're congruent by the SSS congruence theorem, the first one we learned. So example 2, they want us to find the measure of x and z. Once again, this is an isosceles triangle where xz is the base, y is the vertex angle, and x and z are the base angles. We know that this triangle adds up to equal 180 degrees, okay? Total. So if 50 degrees of it is in the vertex angle, the bottom two angles are going to be split between 180 minus 50 is 130, okay? I'll write that down. I did 180, sorry, not 150. 180 minus 50 equals 30, okay? So we know, equals 130, sorry. So we know that 130 degrees is going to be split perfectly between these two angles. If you split something perfectly in half, we could just simply divide it by 2. So we know that angle X, the measure of angle X equals 65 degrees, and the measure of angle Z equals 65 degrees. Okay. I hope that made sense. Pretty basic again. Let's keep going on to example 3. Find the values of X and Y in the diagram. So to find the value of X, we'll take a look at this triangle right here. It is equiangular, which means it is also equilateral. So all sides are going to be congruent. So X is going to equal 7. Okay. To solve for Y, we're going to take a look at this triangle, which does not show that it's equiangular, but it does show that the two base angles are congruent, meaning it's an isosceles triangle. And isosceles legs are congruent. So we know that this line and this line are congruent. So we know that this line is going to have to equal 7. So 7 equals Y plus 4. If we subtract 4 from each side, these 4's cancel out, and 3 equals Y. Okay. We're flying through this lesson. Let's go ahead and just wrap it up with example 4, which will take us maybe a few more minutes than the rest of them. Okay. Example 4 says diagonal braces AC, right here, and BD are used to reinforce a signboard that advertises fresh eggs and produce at a roadside stand. Each brace is 14 feet long. So we know that each of these brown lines are 14 feet long. So we also know that they are congruent, right? Both the brown lines are congruent. What congruence postulate can you use to prove that triangle ABC is congruent to triangle DCB? So we have those two triangles. We know that these brown lines are congruent. We also know that since both of these are 8 feet, that those lines are congruent. And they share a common side right here, CB. So we could use the side-side-side congruence postulate. Ooh, earlier I said theorem. It's definitely postulate, so don't make that mistake. So side-side-side congruence postulate is what we would use. Now they want us to explain why BEC is isosceles. BEC. Well, we established that this triangle right here, I'm going to go ahead and draw it blue and draw the other one red. We established that the blue and red triangle are congruent. Therefore, we know that since those two triangles are congruent, that angle C and angle B would also be congruent because corresponding parts of congruent triangles are congruent. I'm going to erase these triangles now. But we know that these two angles are congruent. So let's go ahead and write that down. DBC is congruent to ACB since corresponding parts of congruent triangles are congruent. Now, we're ultimately trying to show that BEC, this triangle right here, is isosceles. Well, we know these base angles are congruent, and we know that the converse of the base angles theorem says if the base angles are congruent, the sides opposite them are also congruent. So we can say that CE is congruent to BE, or BE is congruent to CC by the converse of the base angles theorem. Okay, now that we know that the two sides are congruent, this side right here and this side right here, I'm not going to leave that on there, but we know those two sides are congruent, that implies that triangle BEC is isosceles. Okay? Now lastly, they want to know what triangle would you use to show that AED is isosceles. AED is isosceles. We used this triangle and this triangle to show that this top one was isosceles. So we're going to actually probably use like the opposite or a different set of triangles to show that this is isosceles. And to do that, we have to look. We know the brown lines are congruent. We know the 8s are congruent. What triangles contain both the brown line and the 8 and share this common side? I'm going to go ahead and draw it in blue. Okay. DCA has the 8 and one of the brown lines. And then I'm going to draw the other one in purple. Okay. ABD also has one of the brown lines, an 8, and shares a common side, DA. So those are the two triangles you would use to prove that AED is isosceles. Guys, that's today's whole lesson. That was pretty quick. Anyways, I hope everybody's doing fine. I love teaching you guys geometry. Keep up the hard work, and I'll see you later. So, see ya!